All right, everyone, welcome to our first lesson on laws of exponents. So this will be a review for you. You would have done exponent laws in grade 11, whether you took functions or mixed math. Here on my website, I'll take you through our learning goals, a little bit of quick background knowledge, and then I'll jump into the lesson. This lesson is going to be broken into several videos just because there is a lot to it. There's several components and I don't want to make each video too long. So it'll be broken up. And our learning goal for all the videos will be to apply basic exponent rules to questions that contain both integer and rational exponents and rewrite exponential expressions in radical form. So there's a lot there. Let's start with apply the basic exponent rules to questions that contain both integer and rational exponents. By integer, I'm referring to exponents that are either negative or positive whole values. So that means we're going to be dealing with exponents that could be -3, for example, or +3, or -10 or +10. It won't be any decimals or anything like that. It'll just be whole values that could be either negative or positive, including 0. Okay, so we can have an exponent of 0. With respect to rational exponents, anytime you see the word rational in this course, we're talking about fractions. So the word ratio is in the word rational, and that's exactly what it means. A rational, just think of it as a fraction. So we're going to be dealing with exponents with fractions as well. And then we're going to rewrite exponential expressions in radical form. And so all that means is we're going to take an exponential expression, so some sort of expression that has exponents, and we're going to write it in what's called radical form, which is with a root bracket. All right, so that'll be in a separate video. A little background knowledge here on my website. I won't spend too much time here because you can read this. But remember that an exponent of a number says how many times to use the number in a multiplication. So for example, in 8 squared, the 2 says to use 8 twice in a multiplication. So 8 squared becomes 8 times 8. 8 cubed, or 8 to the power of 3, would be 8 times 8 times 8. Okay? So where does this come in handy? Why do we learn exponent laws? Well, it particularly comes in handy when simplifying variables with exponents. So for example, is there a way to simplify, so when we're not using numbers and we're using letters or variables instead, is there a way to simplify x cubed times x to the 4, for example? Is there a way that we can simplify that down? And this simplification is used all the time in the derivation of formulas that we use every day, that are programmed into our devices all around us. For example, our GPS devices in our phones. There's mathematical formulas going on behind the scenes, and these mathematical formulas have been developed over time. And part of their development and how they get developed is there's a simplification that happens. There's variables with exponents that need to be combined. And in this lesson, we're going to learn how to combine those. Okay, I'm not saying that you're ever going to go out and derive formulas necessarily. You're not going to really do that. But it's important that we have this basic knowledge in order to do so. All right, and there's a link there to what's called a time dilation derivation. I won't open that up, but you can take a look at that, and just to look at how much algebra is involved in deriving or coming to a formula that we use all the time. So without further ado, let's get right into some of the exponent laws. So let's get into our lesson. All right, so there are 1 law, 2, 3, 4, 5 laws that we're going to go over in this video. All right, so let's start with the first one. Multiplying powers with the same base. So here we have 2, that should say 2 cubed times 2 to the power of 4. I'm not sure why that is written the way it is, but that should be 2 to the power of 3 times 2 to the power of 4. All right, so now we're going to be developing the law here. So in order to develop it, let's expand out what 2 to the power of 3 times 2 to the power of 4 really means. So 2 to the power of 3 can be expanded by writing 2 times 2 times 2. All right? And then times 2 to the power of 4, that can be expanded by doing 2 times 2 times 2 times 2. So here you have the 2 cubed, and then times 2 to the power of 4. So we basically just have a whole bunch of 2's being multiplied together. Well, how can we write that as a single power, right? If we have, well, let's count how many 2's we have. 1, 2, 3, 4, 5, 6, 7. So if I have 7 2's being multiplied by each other, I can rewrite that as simply 2 to the power of 7. So here's one of our laws, right? So when you're multiplying powers with the same base, by the way, in the expression 2 to the power of 3, the 2 is the base and the 3 is the exponent. So when we multiply the same base, meaning I have a 2 here and a 2 here, there's a little trick that we can do to simplify it down to a single base. And you might already see what the trick is, okay? But we'll develop it in a second when we get down to this point. All right, let's go to the next example. We have 3 squared times 3 cubed times 3. And I like that. I like this example because often students will forget that there's actually an exponent on that 3, right? When we say the number 3, you don't write out the exponent, but there is an exponent. And the exponent is a 1. All right, so 3 to the power of 1 is just 3, and that's why we just say 3. So let's expand this out. We've got 3 squared, which is 3 times 3, times 3 cubed, which is 3 times 3 times 3, and then times 3 to the power of 1, which is just times 3. All right, so how many 3's do we have? We have 6 3's, so it can be rewritten simply as 3 to the power of 6. You don't need to write all of this out when you can just write 3 to the power of 6. All right, let's see how this works with variables, because remember what a variable is. I think there's often confusion and nervousness when it comes to letters instead of numbers. And don't be scared. A letter just represents a number. That's all. And if they're both the same letters, like in this case, they're both p's, all right, and that's p to the 5 times p squared. If they're both p's, that means that they represent the same number, which means that they are the same base, all right? If they're different letters, that means they represent different numbers, and they're not the same base. All right, so take that information in for a sec. A letter just represents a number, and if you have more than one of the same letter, okay, that means they represent the same number. All right, so let's expand this out. P to the 5 becomes p times p times p times p, and then times another p, times p squared is 2 more. There's your p to the 5, there's your p squared. How many total p's do we have? P to the 7. So what pattern have you noticed? I'm sure you've probably noticed that you can add the exponents here. Okay, so when we multiply the same base, we can add our exponents. And produce what's called a single power. All right? Right there, a single power. Okay, so let's keep going. All right, let's get on to exponent law 2. And I'll go quicker here because I think we're getting the hang of it. So this time, we're going to deal with dividing the same base. All right, dividing powers with the same base. So we have 8 and an 8 there. That means they're the same base. And that should say 8 to the 5 divided by 8 to the 3. So let's write this out as a fraction. We have 8 to the 5 means 8 times 8, 5 times, divided by 8 cubed. So how do we write this as a single power? How do we simplify this down? All right, well, we know that an 8 divided by an 8 is just equal to 1, right? So let's say that this 8 is divided by this 8, and they actually do what we call canceling each other out. But they're not really canceling. Like, it doesn't end up equaling 0. It just ends up being 8 over 8 is just 1 over 1. And 1 times anything, you don't have to write 1 times anything, right? Because 1 times 4 is still just 4, for example. Or 1 times 8 is still just 8. So let's say that this 8 and 8 will cancel each other out and become 1s. This 8 and this 8 will cancel each other out and become 1s. This 8 and this 8 will cancel each other and become 1s. And what we're left with is 2 8s being multiplied by each other. So we get 8 squared as a single power. 6 to the power of 4 divided by 6 to the power of 1. Okay, I'll go quicker here. 6 to the power of 1 means 6. Just a single 6. Cross off this 6 and this 6, and you just get 1 over 1 there. And what we're left with is 3 6s being multiplied by each other. So it equals 6 cubed. Lastly, p to the 5 divided by p squared. All right. So now this is with variables, right? Nothing changes just because we're using letters. All right. The same laws still apply, right? Because when you're deriving formulas, you don't know what the numbers are, right? You're just deriving a general formula with letters where, people can plug numbers in or substitute numbers in for letters. So when you're working with equations, you're almost never working with actual numbers. You're working with variables or letters. All right? Okay, so p over p would just be 1 because remember they represent the same number. So let's say p represented 3. Well, 3 and a 3 there would cancel each other out and just become 1. Cancel those out, and what you're left with is 3p's or p cubed. All right, so what pattern can we see? Well, hopefully you figured out that you can subtract the exponents when you divide, right? Hopefully you figured out the pattern. You can subtract the exponents. So when dividing the exponents, the same base, we can subtract the exponents and write again as a single power. Okay, so there's our 2 first laws there. Let's keep going. And now let's look at a power of another power. Okay, so let's take a look at this one now. So again, this isn't written correctly. It should say 4 cubed brackets with a squared outside of the brackets. So how do we write that as a single power? Well, let's expand it and then we'll be able to determine that. All right, so 4 cubed, let's start with what's in the brackets. 4 cubed is 4 times 4 times 4, right? But then it's saying to square that. That means we're going to do 4 cubed twice. So we're going to multiply it by another 4 cubed, or 4 times 4 times 4. Did you see that? Okay, so it says to do 4 cubed, inside the brackets, we're going to be doing 4 cubed. But then outside the brackets is a square, which means we have to do 4 cubed a second time. Okay? So How many 4s do we have now? We've multiplied 4 times itself 6 times, so we have 4 to the power of 6. Hopefully you can see already what the pattern is going to be when you have a power to another power. Okay, let's do another example. So 7 squared to the power of 4. Well, what that means is 7 times 7, which is 7 squared, but then do it 4 times. So times another 7 times 7, times another 7 times 7, times another one. So how many 7s do we now have? We've multiplied 7 times itself 8 times. All right, so again, hopefully you can recognize the pattern. Lastly, now with a variable, we have y to the power of 4 3 times. So we're going to do y times y times y times y, so that's 4. But we're going to repeat that 3 times. Okay, so obviously you can see this gets pretty annoying. And that's why, and I'll just do this down here. That's why we want to use our exponent laws, right? So imagine you're, developing some complicated formula, and there's all these exponents, and you don't want to be expanding all of these out. You want to have a set of rules, that you can follow that make things more efficient, right? And so what we have now is a total of 12 y's, okay? And what pattern can you see? Hopefully you've noticed that when there is a power raised to another power, we can simplify by multiplying the exponents. Okay, that was our third law. Let's keep going. Okay, so now we're getting into some more complicated questions. All right, so power of a product or a quotient. So now we're combining things. So we might be multiplying the same base, but then they also have a power above another power, for example. All right, so we're going to be combining it. So let's start with a straightforward example that a lot of students get confused with. Bracket 2a squared. Before we start this, I want to ask you, is 2a squared without brackets the same as 2a and then brackets squared? Are those the same? That's my question. Okay. The answer is that they're not. All right. So let's look at this one here. It says that it's just 2a squared. So that means the squared only is the exponent for a, right? Because it's only above the a with no brackets. But in this example, we have a squared, but it applies to everything inside the brackets, including the 2. So it applies to the 2 as well as the a. Remember that an a just represents a number, right? So it's like saying, let's say a represented 3. It's like saying 2 times 3, right? Because if you have a 2a, it means 2 times a, all right? So how do we expand this out? Well, let's take a look. We have 2a, so 2 times a, okay, squared, so 2 times a again. How do we write that as a single power? Well, we have 2 times 2, which is 4, and then a times a, which is a squared. So it makes sense that this becomes, if the 2 applies to everything in the brackets, if we wanted to drop the brackets, we would have to do 2 squared, right? Because it applies to the 2 there, and a squared. Well, 2 squared is 4, and then a squared we just keep the same. Okay? So that's a tricky one that a lot of students get wrong. Now let's try another example. Remember that this 4 applies to everything inside the brackets. Everything. And what we have here is a power to power situation, right? We have an exponent to the power of another exponent on the outside of the bracket. So it's like saying x cubed to the power of 4. That's what it's like saying. So it's like saying x cubed to the power of 4 times y squared to the power of 4. The 4 applies to everything inside the brackets. It's a power for everything inside the brackets, the x and the y. All right, and now we just use our power to power, which is multiply the exponents. So you get x to the 12 times, but I don't have to write the times. It's understood if I just write y that it's times y to the power of 8. So multiply those, multiply those. Okay? So remember that if you have a power to a power, that outside power applies to everything inside the brackets, if there are brackets, of course. All right? So same thing with this question, the next question. There's brackets, and there's a cubed outside the brackets. That cubed applies to everything inside the brackets. So it applies to the 2 as well as to the 5. So it's like saying 2 times 2 times 2, so that's 2 cubed, over 5 times 5 times 5. Also, the 5 is cubed, everything inside the brackets. All right? And what that turns into is 2 cubed over 5 cubed. All right? Now, that's not written as a single power. That's my bad. This is a more complicated example. It's not written as a single power. But, if you were to write 2 cubed over 5 cubed, since we have numbers there, I mean, that would just equal 8 over 125. If you were to do those on your calculator, 2 cubed is 8, 5 cubed is 125. All right? But now let's look at an example. So this is not a single power, right? A single power is something like this. That is not a single power, but it's a more complicated example that I thought was important to show you. Now, what about with variables here? Right? So same rules apply. You can see that we have a power to a power here. All right? So we have an a squared with a 3 on the outside. So that's a power to a power. But we also have a power to a power here. Because remember, this 3 applies to everything inside the brackets. It's a power for everything inside the brackets. So let's use our, if we do, I won't expand this out totally. I'll just kind of do an abbreviated version, but it's a times a. I'll expand it out totally. It's short enough that I can do it. It's a times a, which is a squared. But then we got to do that 3 times. So times another a times a times another a times a. Right? On the bottom, we have b cubed, so b times b times b, but then we got to do it 3 times. So, I mean, that gets complicated, right? Why not just use our power to power rule and multiply 3 times 2, which is a to the 6, right? 3 times 2. Let me just erase this and make this a little more clear. Okay, so 3 times 2, which is a to the 6. And then do 3 times 3, which is over b to the 9. So notice I kept the fraction there because you can't just get rid of the fraction there. So it just becomes a to the power of 6 over b to the power of 9. And all I did was I multiplied the exponents because it's a power to power situation. Okay? Okay. Maybe here I'll do what pattern can be seen. I mean, there's not a particular pattern necessarily. How about I use this space to do a more complicated question? So how about what if I had 2 4a squared divided by 4b cubed, all to the power of 3. Okay, so we have a power-to-power situation. And remember that this 3 belongs, it's a power for everything inside the bracket, okay? Including the numbers, so including 2 and including 4. Currently, what exponent is on this 2 right now? Right, because you don't see an exponent there, but what number is there that you don't typically show? A 1. So you have 4 to the 1 and you have 2 to the 1. So here we're just going to use our power to power rule. All right, so remember, power to power rule, you multiply exponents. So I have an exponent of 3 here, an exponent of 1 here. So that's going to become 2 to the power of 1 times 3. And I'll actually write that out. And then I have an a squared to the power of 3. So that becomes a to the power of 2 times 3. Now I have a 3 and an exponent of 1 on the 4, so it becomes 4. Notice I write the 4 in the exact same spot, to the power of 1 times 3. And then b, 3 times 3. So see how that exponent applies to everything inside the brackets. Often students will forget that it applies to the 2 and the 4. That's the big one where I'll see a real common mistake is that you forget that it applies to both the 2 and the 4 as well, right? So what you end up getting is 2 cubed, a to the power of 6, over 4 cubed, b to the power of 9. And I can simplify that further because I can do 2 cubed on my calculator, for example. It's 8 times a to the power of 6 over 4 cubed, which is 64. So 64 times b to the power of 9. And notice I'm saying times b to the power of 9. Do you have to write a times sign in there? A times symbol? No. If you just write 64 b to the 9, it's understood that it means 64 times b to the 9. Now, could this be reduced? Yes, it can, right? Like, this is where we take it a step further. All right, so, and this would be, you know, I probably wouldn't mark you wrong if you got it to this point. This would be perfect, but to take it one step further, I can reduce 8 over 64. 8 over 64 is what? 8 goes into both, and it becomes 1 over 8. So I end up getting 1a to the 6 over 8b to the 9. So these are equivalent, right? Like these mean the exact same answer. One is just further simplified. And then I guess, you know, do you have to show this 1 here? No, right? You don't need to show a 1 in front of a variable. So if I were to even take this even further, my final answer would be just a to the 6 without the 1, because it's understood that the 1 is just 1 times a to the 6, which is just a to the 6. And over 8 times b to the 9. All right, but if you get it to this point, that's extremely good. Extremely, extremely good. I'm really satisfied. All right, and now let's just do our final example or exponent law, and that is working with negative exponents. Okay, so if you have 2 to the 1, for example, divided by 2 to the 4, we know that we can expand this out and write it as 2 over 2 times 2 times 2 times 2. Well, now if I cancel out these 2's, I have no more 2's in the numerator in the top of my fraction there to cancel out. So all I'm left with is just like a 1, because 2 over 2 is just equal to 1 over 1, right? So I'm left with a 1 in the numerator. So I'm left with 1 over 1 times 2 times 2 times 2. But I don't need to show the 1 there. I don't need to show it, because 1 times 2 times 2 times 2 is the same as 2 times 2 times 2. So I can just do this. So a lot of students get confused as to where this 1 comes from, right? And it comes from the fact that 2 over 2 crosses off. And they don't just, like I said earlier, they don't just disappear when you cross them off. What's left behind are 1s, because 2 over 2 is 1 over 1. It's the same thing. So that's why there's a 1 in the numerator left there. All right, so how do we simplify this? Well, it simply becomes 1 over 2 cubed, or since we can do 2 cubed in our calculator or in our heads, it's 1 over 8. All right. So what happens if you didn't see this and let's say you didn't see 2 to the 1 over 2 to the 4. All right. Let's just say that you saw something like 2 to the negative 3. All right, 2 to the negative 3 is actually equal to 1 over 2 cubed. So I probably just maybe blew your mind a little, got you pretty confused. Let me prove this to you, that these are actually equal to each other. All right, if you pull out your calculator now and you do 2 to the power of negative 3 in your calculator, you would get 0.125. Okay. Now, if I told you to do 1 divided by 2 cubed, okay, on your calculator, so 1 divided by 2 to the power of 3, you would also get 0.125. You would get the exact same answer because they're equal to each other. They're equivalent. So when we see a base with a negative exponent, like for example, 2 to the negative 3, when you see a base with a negative exponent, we want to convert that. We don't like in math showing negative exponents. You want to convert that to be a positive exponent. And the way you convert it is you simply flip and you take, because 2 to the power of negative 3 is really 2 to the power of negative 3 over 1. That's what it really is. We don't show that 1 there, but now to show it as a positive, the trick is flip that fraction and make the exponent positive. So you get 1 over 2 cubed. All right, and you get an equivalent expression, but the benefit is it now has positive exponents. Okay, so for example here, right, if I were to apply my exponent laws, right, so let's not expand it. Let's do this the way you would do this without expanding using exponent laws. Well, I'm dividing the same base, right? Dividing the same base, 2's. So remember, one of our laws is when you divide the same base, you subtract the exponents. So you write it as a single 2, and you do 2 minus 4. So you write it as a single power, a single base, 2, and then to the power of 2 minus 4. And what you get there is 2 to the negative 2. All right, but we don't like our answer in math to stay as 2 to the negative 2. So remember, flip it. So remember that this is really over 1, right? Flip it, it becomes 1 over 2 squared. So the negative 2 became a positive 2 when I flipped it. And now I know what 2 squared is, so that's fantastic. I know that it's a 4. So I know that 2 to the negative 2 is actually 1 over 4. All right. Okay, let's do this one again. Last example here, using our exponent laws, we're dividing the same base, so I'm going to write it as a single power, a single 2, and do 3 minus 4. Subtract the exponents when you divide. You end up getting 2 to the negative 1, right? 3 minus 4 is negative 1. But we don't like to leave our answer like that. Okay, we don't like to do that. So I know that this is really over 1. And now I flip. 1 over 2 to the power of positive 1. which is just 1 over 2. All right. So what could we say about this final exponent law here? When dividing the same base subtract the exponents. Right? We know that. So this we know. Okay. If we are left with negative exponents, okay, move the power to the denominator, so flip it basically, as a positive exponent. So remember that, and this takes practice, okay? So that's all this is you just got to keep, it's repetition, you got to do this over and over again. Some common mistakes I see, like if students see 2 to the negative 1, all right, what they forget to do is bring the 2 down with the exponent, right? Notice I bring the 2 down as well. Sometimes students don't realize that, right? And they get confused and they kind of shut down at that point. This whole thing is over 1. And if we're flipping that, I have to bring the 2 with it. Okay? You've got to bring the 2 with it. Okay? So